Welcome to Let's Get to the Marks. All right, yeah. Question 3. This is on halogenoalkanes. So why don't you grab a pen, grab some paper, pause the video, have a go at this question, and then unpause and watch the explanation. All right, this question's about 1-iodopentane. I'm going to go through the explanation here. We got the structural formula. 1-iodopentane can be hydrolyzed by aqueous sodium hydroxide. Outline the mechanism for this reaction, include curly arrows, relevant dipoles, and the final products. So here they've given us the formula for 1-iodopentane, and they want us to show what happens when it reacts. They want us to show the mechanism with sodium hydroxide. Now, we're not so much interested in the sodium. That is playing a bit of an irrelevant role here. We have got our hydroxide ion. And the key here is the hydroxide ion has a lone pair. It's actually got a couple of lone pairs, but only one of them gets involved here. And it's also got a negative charge. Doesn't really matter where you place that negative charge, but I'm going to put it near the lone pair. Okay, so this hydroxide ion is going to approach our lovely jubbly 1-iodopentane. What's it going to do next? Well, it's going to be attracted to part of this. Do you know which part it's going to be attracted to? Well, iodine is a halogen, and halogens are electronegative. We give them this little delta minus symbol, and meaning sort of slightly negative, and we give this one a slightly positive symbol. Now, you might be tempted to do that. That would be incorrect. Why is that? Positive charge cannot move. It's the lone pair of electrons that can move. Remember, positive charge tends to be in the nucleus trapped as protons. It doesn't move. So we want to do a curl in our arrow, a slight curl, and we definitely want to end up there. It's got to at least have a curl. That's not a very good curl, but I might get away with that. Okay, it should be a bit more curly. So maybe I'm going to redo that one. Let's redo it just in case my examiner doesn't like that, the state of that. So let me give it a bit more of a curl. Oh my gosh, that was even less of a curl than before. And then the second arrow I need an arrow coming from the bond, that it's best to touch the bond and going to the eye. And that shows that this bond is breaking. Remember, this is a group 7 element. It can only have one bond. This is a group 4 element. It can only have 4 bonds. So the fact that we're reforming a bond here, it cannot maintain that 5th bond. Okay. So this is all looking good so far. We've got the lone pair and the negative to get the mark. We've got the curly arrow. Beautiful. You might even, is this a nucleophile or electrophile? Well, it's attracted to positive charge, so it's a nucleophile. And then we have the curly arrow going from the bond to here, and we put the positive and negative charge there. Bosh. Now there's a third mark. They want the final product. I think this is a bit stupid. I think you should get all your marks for what we've done there, because for the final product, you're just really writing all of this out again, which seems to me a waste of an A-level student's time. And you're drawing the carbon, you're drawing the hydrogen, you're drawing the hydrogen, and you're sticking the OH on. So we've now made pentanol, haven't we? And that is nucleophilic substitution. Okay. Oh dear, I can't get this in the right place now, so you're just gonna have to bear with me here, folks. It does say final product, plural. So what's the other product? Well, the iodine's broken off, hasn't it? So the iodine's broken off, so we have an iodide ion, and that is the final product. If we forget that, we won't get that mark. All right, let's move on. So zipping down, 1-iodopentane can also be hydrolyzed by water. So H2O can provide those hydroxide ions, not just sodium hydroxide, using aqueous silver nitrate with ethanol. So ethanolic, um, yeah, as the solvent. A student uses this method to compare the rates of hydrolysis of 1-iodopentane and 1-bromopentane. What measurement and observation would allow the student to compare the rates of hydrolysis? So, what you've got to think about here, guys, is the iodide ion is going to be released when that becomes pentanol. And when this becomes pentanol, you're going to have a bromide ion released. And of course, how do they react with nitrates? Well, or the silver, I should say, from the silver nitrate. Well, you're going to get AgI, and that's a yellow precipitate if you know your halide ion tests. And you're going to get AgBr, which is a cream precipitate. So we're going to get a precipitate formed. So the idea here is what observation would allow us to compare the rates. It's the time taken for precipitate to form. And really, you might do a particular mass of precipitate, you might do a disappearing cross. Depending on how you're going to do this, you're going to get a precipitate forming. So you could kind of do a disappearing cross situation, or you could do time taken for a certain mass of precipitate to form, etc. One iodopentane was found to react faster than one bromopentane. Explain why. Now, a lot of people want to get into talking about electronegativity here. You don't need to talk about electronegativity here. Is electronegativity a factor? Well, you might say bromide ions are more electronegative as you go down the, higher up the group towards the top right of the periodic table. Bromine is higher up than iodine in the non-metals. It's more electronegative, which means this bond is going to be slightly more polarized. And what's going to happen is you might say, isn't that going to attract hydroxide ions more easily, and therefore this would break more easily? It doesn't come down to that. Or some people might say, isn't this more negative, this more positive? Doesn't that have an effect on it? Well, really, it doesn't come down to that. When we're looking at the halogenoalkanes or haloalkanes and seeing the rate of hydrolysis, we're really looking at the strength of this bond. So which bond is stronger? Well, we're going to say the carbon iodine bond is weaker because the CBr bond is weaker. It has, and this is the key, a lower bond enthalpy. And what that means is less energy is required to break it. So less energy is required to break it. So for halogenoalkanes, the speed at which they react is down to the bond enthalpy. And of course, CF bond is going to be the strongest, followed by CCl, followed by CBr, and then Ci. And so you want to be sticking to bond enthalpy and the energy required to break. Okay, I think that may be the end of the question. No, there's more. There's more, folks. The mass spectrum of one iodopentane is shown below. We've got the relative intensity on the left, or the y-axis, and we have the MZ mass charge ratio along the bottom. What information is given by the peak labeled X? So this is your M peak, and this tells us 198. This gives us the MR, the molecular mass. So this gives us the MR. And that's going to get us a mark. Now, this tiny little peak next to it is called the M+1 peak, and that takes account of the fact that there might be a carbon-13 isotope in the molecule. So you always get a slight tiny peak to the far right of the M peak. Okay, let's zing down to the next question. Write the structural formula of the ions responsible for the peaks labeled Y and Z. Y has a MZ ratio of 71 and Z has an MZ ratio of 43. So essentially what goes on here is they get snapped, right? And what are we dealing with? Is this the 1-iodopentane? I did read the question, but yeah, 1-iodopentane. So what all you've got to do in these situations, quickly sketch out your drawing like this, right? I'm not going to bother putting the hydrogens on because it's long. Oh my days, look how long that took. All right, and all we need to do is start here and break, work out the score. So that is 15, 3 H's and a 12. So we get that fragment snapping off. We should expect a peak. Look there, there's a little peak here at 15, but that's not what they're asking us about. They're asking us about this one. But let's keep going along and let's break this bit. This is an ethyl group. So that would be CH3, CH2. That is going to be 14 and 15. That's going to be 29. Look, you'll see there's a peak right about there, 29. But again, we're not interested in that. That's not what they're asking us about. They're asking us about 43 and 71. So let's go to a propyl group. And if you do that, you're going to go, right, that's 15, 14, that's 29, that's 14, that's 39, 43. So straight off, we know this one is going to be C3H7. And then let's look at the 71 fragment. We can kind of work it out. It's going to be, if I add 14 to that, that's going to be 53 53, 57, add another 14, 67, 71. So this is going to be all of this. If you add up all of this, iodine's got something like 80 as its mass number. So neither of these contain the iodine. So this is going to be C5H, um, what's that? 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes. Remember, remember the 5th of November. We do not need to worry about anything else except for the fact that when you break this, you are losing an electron, okay? You're going to lose an electron when you break the bond. And so this is going to have a positive charge and this is going to have a positive charge. And the clue, the reminder is the word ions. So let's not forget that, otherwise we're going to lose the marks. So the ions, these are ions, they're going to have a positive charge. Beautiful. Wunderbar. Right, we're on to C. 2 iota 2 methabutane is an isomer of 1 iota pentane. Draw the structure of 2 iota 2 methabutane. Nice and easy because butane is 4 carbons, right? So that's that bit done. Then we need methyl on the second. So it doesn't matter which end you do this from. Could have done that one there. And then I need iodine on the second because it's 2 iodo as well. So now in the exam, they're going to say, where are the hydrogens gone? So we need to put the H's on. Back in the day, you never bothered with the H's. Back when I was learning, they used to let you do it without the H's, which was nice. But not nowadays. Okay. There we go. Now, it doesn't matter if I use skeletal formula or the displayed formula. I've gone displayed. Suggest one similarity and one difference between the mass spectra of 1 iota pentane and 2 iota 2 methyl butane. So we want one similarity and one difference between the mass spectra of 1 iota pentane and 2 iodo methylbutane. Well, we can say they're both going to have, look, they're both going to have an ethyl group because remember we did it before. They had a methyl and ethyl. So I can just say similarity C2H5 plus. So I can say there's going to be a peak at whatever that is. Peak at, what is that? Ethyl. So that's 29. Bosh. Peak at 29. They both form a C2H5 plus ion. So a peak at 29. One thing they both cannot form though, check this out. This is the main difference. Don't do that, Tom. So what did I say? Peak at 29. Right. So one thing they can't form is a propyl group that 1 iota pentane can form. Let me just show you because you might be like, what the bloody hell is he on about? So let's do this. Oh my days, don't do this, man. Russian, Russian, Russian. This can form a propyl group, right? C3H7 plus. That's the peak at what do we call that? 41. So we get a nice peak at 41. Can't get a peak at 41 here. You might say to me, yeah, you can. You can get a peak at 41. Check this. You can do this, right? Oh, that ain't going to be 41, is it? Because look, that's going to be C3H5. So you're not getting a peak there at 41. What about if you go this way? Can't we get a peak this way? Um, what about that? No, look, we're cutting off that. That's going to be a peak at 40, right? That's 36 for the 3 carbons, 39, 40, 41, 42. So that is going to be, I don't think I can add up. I think I've got some serious issues with adding up. Um, sorry, that's going to be 43. That's going to be one less. Yeah. Oh my gosh, I can't add up. That's going to be 43. And this here is going to be 42. So you can't get a peak at 40. So the difference is into iod. I don't think I've got to write all this out. In 2 iodo, 2 methyl butane, no peak at 43. Gosh, I nearly said no peak at 41, which would be nonsense. But yeah, there we go. No peak at 43. So you can't get that propyl C3H7. What you can get here, this is going to be C3H6. Yeah, I guess +2. And that's what you're going to get there. You're not going to get that. So anyway, enough waffle. Let's get to the marks.
You're still here? It's over.